If I get the host, I'll share.
I'm going to let everybody in a second.
Okay.
I'm going to do that now, and then I will make you hostess with the mostest. Host with the most. You should be host now.
All right. Okie doke. All right, is everyone able to see my screen? Okie doke. Well, let's get right into it. There's a lot of reading in this lab, so I'm gonna get started. The first thing we want to think about here is the idea of pattern recognition. So the human brain, one of my favorite quotes, see if I can get it right. If our brains were so simple that we could understand them, then we would be so simple that we couldn't. That came from Civilization 5, I believe. The reason I like that quote is because it points out that our brains are truly amazing at doing stuff, and we don't even have the faintest idea why, or how, I guess is a better way to say it. Depending on your perspective, the human brain, is created, designed, evolved, doesn't really matter, because we're talking about what its current state is. And the thing that we're so amazing at is pattern recognition. You can definitely see why it's evolutionarily advantageous to be able to see patterns very well. In fact, we're so good at it, we see patterns where sometimes there aren't any. Turns out, actually recognizing patterns and able to, in order to predict the future, is really difficult to codify, really difficult to tell a machine how to do it. Why is that? It's because we're really good at filtering out data that doesn't matter. So if you take a minute to look at any of these patterns here, it shouldn't be too hard. Like, you've been trained since elementary school to fill in the blank. Like, so it basically should be like compulsions. Like, yep, this is F. This is going to be 30. Pattern recognition is built into us pretty well. It occurs in nature. These kinds of patterns all the time. That's why we see them everywhere. Sometimes we even see them where they're not there. Well, how do we get the guess predict to the next step? Is that there's only one possible option? Is it that we have previous items? Or what is it, the relationship between items? So if we're trying to see a pattern in, I don't know, berries on a bush or something, what if we have more than a single sequence? What if we got two sets of numbers? How can we predict the next item in a situation like that? Well, we might already have a tool for that. The thing we've been using so far with trying to fit a line to a scatter plot. So this is the example we're going to be using to try to figure out the output at points in the future. So we've got a speed versus time versus speed, I guess, set of data here. We've recorded time in 1 second intervals, and at those times we've recorded our current speed. So let's see here. We want to do a couple things. first thing we want to do is plot the speed versus time using a scatter plot. Now, this doesn't require a whole lot of remembering, but does anybody remember how we usually do these? How do we build a scatter plot? You don't even have to give me the code, just, describe it. Put in a list of X values and Y values in a function. Yeah, pretty much. A lot of times we get handed this function package that, as long as we have our X values and our Y values in a list, then it does what we want. Okay. So we want to make a speed versus time scatter plot using blue markers. Okay, we can do that. So we're going to get something. All right, what's next? We want to plot a red line on the scatter plot based on the linear model. F of x equals mx plus b. Okay, what does that mean? Someone tell me what number 2 is wanting us to do. The blue marks on here are the scatter plot. Create a regression. I think you're a bit ahead. That's step 3, but that's fine. What kind of regression are we doing today? We're doing linear regression. So what does that mean? It means, what's step 2? Well, we want to get a line on here somewhere. Well, it's red, it's a line. Good job, we did it. Is this line better than this line? I don't know. How does one tell what better means? Well, step 3 says trial and error, find M and B that provide a good visual fit. So we want a red line that, gives us a visual fit that looks pretty good. That's good enough. I mean, we're pretty decent at this task here, our eyeballs and our brains. So now we have a line that we are okay with, and what we want to do is predict what the value is going to be at 15, which is like over here somewhere. So that's what we're going to be trying to do, and it's pretty much going to take the whole lab. Okay. Now we've done this before, and as you can see, most of what we're about to go through is how exactly to do this. So don't worry too much about having to scratch your brains for what's the code. We'll get into the copy paste session a little later. So before we do that, let's get some terminology listed out. The first one I want to talk about is called linear regression. So this is a predictive analytics technique that uses observed data, predict an output variable. Now, what's this gobbledygook? Nothing crazy. Regression simply means use past values that you've observed to try to predict what's going to come next. And linear regression, it means it's going to be some kind of line, y equals mx plus b. And there are many types of regressions. So what is the input? It's called the predictor variable. This is what helps predict the output variable, commonly referred to as x. Generally, this is your most independent variable. So what is less dependent on whatever system you're looking at? Time or speed? Time is almost always your independent variable. And then you have the output variable, also known as the response variable. This is what we want to predict. Okay. So to estimate our output using our linear regression, we're going to use this model, which is linear. So y is the estimated value based on our linear equation. So what we want to do is find statistically significant values of alpha and beta that minimize the difference between the true y output and what we estimate. If we're able to determine the optimum value of alpha and beta, which are here and here, then we got a good line. So how do we estimate them? Well, if you think back to what I was just showing, I got, dots. So can somebody say which line's better? I got a blue one and I've got a green one. Which one's better for the red dots? The green one. Now, why is that? Well, I could try to explain why, but I don't really need a big explanation. It just looks better. It looks better. It seems like it's going in the direction of the dots. And in this instance, it's one of those things where you trust your gut. My brain's telling me that the green line is a closer fit. Okay, so if that gut feeling seems to be correct, let's investigate it and see why it is that way. Well, there are a lot of ways to determine what kind of line is better than another. And once you have a method of, let's see, let me get those back up if I can. Undo. Yeah, there we go. Once we have a method of one line's better than another, right? So what's better, the blue one or the green one? Neither one's perfect, but the green one's better. Okay, so now I can say this one or this one's better. Cool. All right, let's try a new line. My current good one is the first green one, and then I made a second one. So which one's better? I'm going to use the same metric I just did. Let's say that the second one's better. Okay. Okay, do the same method again. I've got my current best one, and I've got a new one. Which one's better? And we're going to repeat this operation until we find the best one. We've gone as far as we want to go. Now, if we actually formalize the definition we have for better, now there's a lot of ways to do it. Let me set this to bright mode real quick so we can read the equation and burn out our retinas. Once we have a measure of given two lines, which one is better, it all falls into place. Now, this current method is called ordinary least squares. Simply means you've got your line, you've got your data in red. Measure the vertical distance between your data and the line at that particular point in time. Take the distance of all of them. And what we're going to do is we're going to plug them all into this formula, get them all collected, and then we're going to normalize, and we'll have a number to say, this is how far this line's off, this is how far this line's off. Take the one with the least number, and then repeat. So we want to find values of alpha and beta that minimize the sum of the squared differences. What does that mean? Here's the difference, and we're going to square them. It's not, may sound confusing, but it's quite simple. Again, this is something I've been answering in office hours, and I'm happy that people are curious, but this is not a math class. And by that, I mean, it's not the mathematical theory is not something you need to worry about. So you just basically have to trust that these formulas work and what they're good for. You don't need to worry about how they're derived. Usually in the math classes where they are derived, that's the whole lecture for the day. Is the whole 90 minutes is we're going to derive this equation. So if that sounds fun to you, talk to me, and maybe you might want to be a math major. But anyway, so beta in our formula is going to represent this. So this is the current X item we're looking at. So let's say we're at position 2. X is 2, and the Y data is like 5, and our estimated is like 6.5. So I is 2. So X2 just so happens to be 2. We're going to subtract the mean of the X's from it. We're going to take the current Y, and we're going to subtract the mean of all the Y's from it. Sum all that up, and we're going to divide that whole thing by the sum of the squares. Alpha is simply the mean of the Y minus beta times mean of the X. Now, what this actually is the covariance of X and Y. So right here, This is the covariance. Now, if we think back, what did we use the covariance for? Well, we used it to make correlation coefficients. So in some way or another, through some mathematical magic, this is something that relates how related X and Y are. Okay. So here's a brief recap on correlation. I'm going to switch it back because this is bright. Brief recap on correlation. Things, so if you have two or more variables, we can say they are correlated or not correlated. We can assign a number between -1 and 1. -1 meaning they are negatively correlated, 1 meaning they're positively correlated, and 0 meaning they're not really correlated at all. And we use those to get the Pearson's coefficient R. Okay, so we have all the methods we need to actually do our example. So we've got our data. Cool. Let's make a data frame out of it because those are useful. We're going to hard code in the data. So we've got our time, we got our speed. Cool. We're going to make a data frame out of the dictionary made from these. All right. I think I restarted my kernel. Yeah, I did. Okay. All right. Data frames out. Let's look at some statistics for it. We got a mean here for both, standard deviation for both. Everything's looking fine. Okay. We are going to want the variance for both of them. And that's useful because we want to know, is there a relationship between time and speed? Are they completely independent? Do they have some kind of relation? Let's use the covariance to answer that. What's the covariance between time and itself? Something silly. What's the covariance between speed and itself? Something silly. Covariance is difficult to read, which is why correlation is so much nicer. So using the Pearson method we just talked about, we have now the covariance and the correlation of time and speed together. One of the reasons the correlation is so nice is because at the end of the day, we're trying to ask the question, do X and Y have some kind of relationship, I guess? Is one dependent on the other? To me, looking at this box is much more informative, at least quickly, to answer that question than this box. Because what's the correlation between time and itself? Well, obviously, it's going to be 1. It is itself. What's the covariance between time and itself? Turns out to be 11. What the heck does that mean? It's kind of complicated. Covariance is a lot like well, the variance, huh? Because it's a ratio and doesn't have a unit. But with the correlation, we can see, well, speed and time seem to be pretty correlated, and speed and itself are perfectly correlated. This makes sense to me. Everything on the diagonal is going to be 1. Okay, so now we have our correlations, and now what are we going to do? We're going to do the method of here's a line, here's a line. Which one's better? Okay, well, let's say that one. All right, here's a line, and here's a line. Which one's better? Okay, let's say it's the new one. All right, and we're going to play this game until one of two things. Well, yeah, one of two things happens. Either we reach a number in our total error that's small enough that we're satisfied, or we reach a number of steps in this game where we say don't do any more. So only try to get the better line 50 times. Because if you were to say only stop once the line's perfect, you may never stop. Probably, in fact, you'll probably never stop. Okay. So we need to calculate the X mean and the Y mean. Pretty simple. We've got 2 methods for that. We want the covariance to put into our data here. And then we want to get our alpha and beta from before. Now this box here is just taking all the formulas we've been talking about like this one and this one, and just putting them into variables. So it may look kind of confusing, but it's really not. Alpha, remember, was the mean of y minus the mean of x times beta. And what was beta? Well, remember, it was this big sum on top of a sum thing. Well, it's not really that scary. It's right here. We got a sum of one thing times another divided by the sum of something squared. All right. Well, let's see if we got the sum of the covariance is one thing times another. And then we have the sum of this squared. So here's that, and here's that. All right, we got our beta, we got our alpha. So this gives us an estimate. Plug these in, and we say, I'm going to approximate my function as y equals, let's say, 12x minus 16.5. Let's see how that works. Okay, so with our prediction line, these are the values that we get as output. Let's plot it and see what happens. Hey, that's not bad. Of all the lines in the world, this one's better than most. So this is our line of best fit. We can see from this that there's a positive linear relationship between x and y. And using our model, we can predict y for any value of x. So what if I want to know what's the value of at time 20? Well, we can do that. I can't use the blue data to give me that because I don't have data for it. But I can use the red line, which extends forever. This isn't just, it's not just here. It goes all the way off the screen. But so using that line, I'll plug in 20, see what I get. So according to our prediction, at time 20, our speed should be 222.6. All right. So that is a very quick and dirty, well, I guess not dirty, linear regression. And lo and behold, this is what you're going to be doing here. Now, all of these, pretty much everything we're going to do for the homework, we're about to go through in the lab, but the method's the same. So any questions before I get into that? Okay. So what method did we use? It's called OLS. I forget if it was actually given what the acronym means. Don't know. But if you remember a couple labs ago, we did like 18 cells in a row that were just basically derivations of the two cells that did all the work. Same thing here. So we did the almost manual method of OLS. Cool. Well, let's see how we would actually just use the OLS method if we just wanted to use it rather than see how it works. Well, there's this nice library, stats models. We're going to import it and we're going to give it a moniker. And what we're going to do is we're going to take our formula where x is the predictor variable and y is the output, and we're going to fit it using the fit method. All right. So let's see. Our data. This is just going to be standard construction, I believe. I want to try something before I run this. Data. All right, that's our data frame. Okay, so this is kind of a funny quirk of Python. I'm saying model is equal to something, whatever this something is. What the heck does this mean? Does anybody know? Why on earth am I saying data equals data? Oh, ordinary least squares. Yeah, you're right. Why on earth am I saying x equals x, data equals data? That doesn't make any sense. Of course, x equals x. Even if you don't know for sure and you have a feeling, what do you think it is? Is it a keyword in the function? Something like that, yeah. So what's going on here is the function x, y, z. Let's say my function I've defined like this, and I want to return x plus y plus z. Who cares? All right, that's fine. But what if I have in my data something already equal to x? Well, that's what we have going on here. One of the inputs is called data, and it just so happens that our data frame is called data. So we're saying the data that the function is expecting, it's actually going to be using the data frame called data. It's just a coincidence that they're named the same thing. So this isn't nonsense. This is because of scope. There's two different datas. One's our data frame and one's the thing the function's expecting. All right. All right. It went from busy to idle. So it actually ran, it actually did something. We no longer have to calculate alpha and beta ourselves because it does it for us. Let's check out what they might be. It's saying approximate time at 1.97, intercept at negative 16.7. That's pretty close to what we had. Here. Pretty close. In fact, I think they're exactly the same. All right. Let's see what that looks like. Looks pretty similar. So, how good do we feel about this? Well, the OLS method seems pretty simple. What is a method for doing any of this? It's anything that can tell you what line is better than another, even if your method is not very good. So I've got two lines. Which one's better? I don't know. Flip a coin. It's a terrible method, but it's still a method. If my method were whichever one is newer, I can still work with that. Would I trust that? No. What is our method? Take both lines, calculate the ordinary least square, pick one that's better. All right, let's actually use this for some real data. Okay, we have a data set of spendings on TV, radio, and newspaper advertisements and number of sales for a specific product. So we've got advertisements out on TV, radio, and newspaper for widgets. And we want to know how many widgets did we sell from TV, radio, and newspaper ads. We're interested in exploring the relationship between this and the following question. Can TV advertising spending predict the number of sales for widgets? The reason I say widgets is because it's easier to, at least for me, we've got a widget factory. They make widgets, but they need to sell the widgets using some advertising. They use TV, radio, newspaper. Can we use any of these to predict the number of sales on our widgets? Can we use the three of them together to predict the number of sales for our widgets? And finally, what's the best way to predict widget sales? Well, let's answer that. What are we doing here? Well, we're getting our data from this URL using requests. Done. Let's see. We are going to make a data frame because data frames are nice. We're going to look at the statistics. We got. So why do I usually do the describe method? Because if I see one of these missing, I know maybe one of the data didn't get converted to numbers or something. All right. Now we're going to put these NumPy arrays. So the series from our data frame, we're going to put those into variables. That's weird. So the same variable name is used here twice. This may cause some issues, and if so, we'll come back and look. Okay. Got our covariance. About the only thing we can say about the covariance is, well, it is symmetrical. 69.8, 69.8, 105, 105. This means it ran, it worked. What can we infer from it? I don't know. Covariance is hard to read. Well, luckily we can get the correlation coefficient. This is much nicer. My brain is still trying to figure out what's going on up here. So this is much nicer. Everything on the diagonal is 1, as it should be. What's the correlation between radio and radio? 1. And then we have some actual correlations, like maybe what's the correlation between newspaper and TV advertisements? Who knows? Okay, now the thing we're interested in asking is, can we use any of these 3 to predict the output of sales? We are not really interested in using the TV advertisements to predict the radio advertisements. In fact, they should basically be independent. And, upon further inspection, if you have this number as a correlation, what would you say between the two things? So X is TV and Y is radio. They have a correlation of 0.05. What would you say about that? Are they nicely correlated? Yeah, it's a very weak correlation. I will. Very well said. Okay. So question 1, can TV advertisement spending predict the number of sales? Well, TVs are input, sales are output. Let's look. All right, we have a model of y equals 7 plus 0.47x. Let's see what that looks like. Kind of looks like that. So blue is the data and red is our predictor. Okay, I mean, it's not the worst thing. I can see how it's trying to be accurate. Okay. Let's try the same thing with radio. Okie doke. So we have radio advertising spending and widget sales. Here we have TV advertising spending and widget sales. Notice that the data may look different. That's because on the x-axis, we're changing what we have in there. Okay, and now finally, newspaper sales. So just using your eyeballs and your brains, which one of these looks the best? Newspaper, radio, or television? Yeah, I think so too. I would definitely be comfortable saying newspaper doesn't appear very correlated. Okay, so I remember this from last semester. Some people had an issue with Sklern. If this cell doesn't work, let me know afterwards. Basically, you're gonna. I'll show you what to do after. All right. So let's do the same thing with this package here. What this is gonna do, something neat. Okay. So we asked, which one's better? This one, or this one? Well, what if we could, instead of saying TV for widget sales or radio for widget sales, what if we could do all of them? This is for our time versus speed, by the way. It's just getting the Sklern up as an example. Let's see. All right, watch this. So this is our linear regression. It's a regression, meaning we're trying to find a best fit, and it's linear because it's a line. Okay. Will it work in a pinch? Sure. But what if we could do this? Which one do you think is better as a predictor of the blue dots? This one or this one? Agreed. Now, what is it that I changed? Well, not a whole heck of a lot. All I did is I went from y equals, where's my, y equals mx plus b. Okay. It works. It does stuff. What if I said y equals, I'm going to add x squared in there. We're going to go up in order. Ooh, what if I want to go up at x cubed? The more x's I have in here, the more computationally intensive, but the better fit I can get. And if it just so happens that it's a line, it's just that the beta 2 is going to be 0. So you don't really, the only thing you lose by going up in like x squared, x cubed is it's going to cost more time to calculate. Okay. Here is the final result of doing that with our speed versus time. Looks pretty accurate, at least to me. This cell here, I haven't figured out what it's for yet. So I was talking with Dr. Cleveland. I think it is just here by accident, so don't worry about it. So we finally have a predictor for our speed versus time. Okay. That is, other than the exercise we're going to spend the rest of the lab doing, which is only like 10 minutes. That's everything. So does anyone have questions? Because this is what we're going to be doing for here. The exercise we're about to do is the same thing for the homework, just different data. That's weird. Okay. So this is going to be one of those, we're going to do this together. I will give the biggest hint I can. Most of this is going to be copy and pasting from different spots, either in the lesson or in the lab. So that's what we're going to try to do. I can run this, the data's there. It exists. And we've got a nice little skeleton of what we want to do code-wise. So I want to read this into a data frame. How do I get my data into a data frame? Why do we want to use a data frame? Well, they have a lot of nice framework around them. No pun intended. Is that a pun? I don't know. They give us a lot of nice tools. So I have some data out there in the form of a CSV. I downloaded it. I have it in a variable. We would like to make it into a data frame. How do we do that? There's a method called read CSV. Thank you, Parth. So let's call my data read CSV. Now I could, this is a short method and it only takes one argument. I could copy this from somewhere else. Let's see, probably near the start. Would have taken me less time just to type it out, but that's fine. Okay. Back to where we were. Okay. We want this to be school to salary. Okay. All right, prints out. We have some data. Is it the right data? Who knows? But it's numbers. All right, we want to make a scatter plot. How am I going to do that? Where might I go look? Up. Yeah, it's up there somewhere. Let's see. First time we did one was about right here, right? So I want a scatter plot. How do I do scatter plot? Well, it's the stuff in blue. So I'm going to want some of this stuff. So we made our data frame. Get these later if we need them. And it looks like this is the stuff we want. Now, what do we need to change? Because you can't just copy and paste. Got to change some stuff. This seems fine. This seems fine. We don't need this yet. And we'll change the labels when we get there. So my plot is taking time and speed. So what do I need to change about these two to make it work with my new data frame? Here's the data. What do I need to change this to? So this is our time, which was our independent variable. What's our independent variable here? Well, what are we trying to ask? Lists of the time and speed from the data frame. You'd be correct, except that we're not looking for time and speed. Our data frame has 10-year salary and annual tuition in school. That's all we've got. That's fine. So we got 10 colleges with salary 10 years after graduation and tuition costs. We want to know what's the better variable as a predictor. Does the resulting model suggest that tuition paid predicts post-graduation salary? So we have three things we can, we have three series here. School, well, I guess we have four, but I wouldn't suggest using this one. The one we want as an output, let's start there. What's the output we're trying to predict? Which actually answers this right here. What is our output? I'm sorry, this is the opposite question. Which variable is the predictor? So what's the input? What's the thing we're going to say, does this affect the output? Is it going to be school? Is it going to be tuition? Is it going to be salary? So the question we're trying to answer, the overall question, is does the model we're about to build suggest that tuition predicts salary? Okay. So we're trying to figure out if something predicts something else. Those two things are tuition and salary. So which of those would we say is the input? Which of those would we say is the predictor? Which is the one that predicts? Tuition. Yep, it's literally right there. So tuition. And I'm pretty sure this is actually, yeah, you got to do that here too. Okay. What's the response? Well, there's only really one thing left. We could go with school, but it's not really numeric. So by process of elimination, we can say that. Okay, so we've kind of answered our own questions here. We want X to be tuition and Y to be salary. Okay, how do I, what do I got to do to get that in there? I got them. I have them. Let's see. Put them in the data frame, right? Did I delete it? Oh, no, it's right here. Yeah, my data frame's right here. It's called my data. How do I get the data for tuition from my data frame here? Well, what kind of thing is supposed to go here? Let's go look to see where we yanked it from. Okay. So you're thinking quite well there, Parth. What goes in it and where we pulled it from? A list of stuff, a list of numeric stuff, preferably. Now, what do we have that we want to put in there? Well, we have a column. What kind of thing is a column? Well, it's a series. Can we plug it straight in there? I don't know. Let's find out. My data. Annual, no, two ends. Tuition. My data. 10-year salary. Turns out you can't. This is one of the nice things about data frames is the series, even though that's not a list, it can be passed around to some plot functions so that you don't actually have to do the method that Parth did, but it's good thinking. Okay, so always stare at the plot. I'll change the labels. So this is what annual tuition, and this is 10-year salary. This is tuition versus salary. Okay. We have scatter plot. Hooray. Well, since we are out of time, would have liked to have gotten through it, but that's how the cookie crumbles. The method I've been doing here is exactly what we're going to be doing for the homework. We've just been given a little more steps. Let's see, how far did we get with exercise 1? Let's see, we got to about here. Well, could be better, could be worse. Anybody have any questions, comments, concerns, observations? Okay, then. Well, you know where to find me. I also have office hours tomorrow. And everybody have a nice day.